3, 2, 1, let's finish this sequence 3, so our third video in our collection on sequences. Alright, so, note, a little bit shorter today, but very nutritious today. It's going to be a small meal, but it's going to be nutrient-dense. Alright, so, what are we talking about? So the last thing to talk about with sequences, before we move over to their cousins series, is this notion of a Cauchy sequence. So what does it mean for a sequence to be Cauchy? Well, give it an epsilon, there is an n, so that x sub n minus x sub n does not exceed epsilon, or n and m get bigger than n. Interesting. Okay, so intuitively what this means is that my sequence, eventually, the terms don't get that far away from each other. So in other words, eventually the terms are clustering together. So that's the main idea here. Now, why is this called Cauchy and not like a cluster sequence? Well, I mentioned him. Cauchy is a very important figure in mathematics, specifically in analysis. So as we noted, the 1800s is where the story of analysis begins, when Fourier decides to add up sine and cosine infinitely many times, and everybody calls bullshit on it, even though he was right. So throughout the 1800s, basically everybody is reformulating calculus and getting it on more firm foundations. And one of the mathematicians that contributes to this story is a guy named Cauchy, also a French mathematician, who is quite the character in math history. He got exiled from France. He came and he got let back in after they kicked him out. And there's a great quote about Cauchy from a Norwegian mathematician, Niels Heinrich Abel. Abel said, "Cauchy is a madman, and there is nothing that can be done about him." And that's a reputation, right? That's how you want your contemporaries to speak of you. So one of the mad things that Cauchy was interested in was this idea of sequences that clustered. And the reason he was interested in this is because convergent sequences, while they're very nice, and while they're clearly something we use a lot of, there is kind of a flaw of them in the sense that you kind of need to know what the limit is in order to make the epsilon arguments work. Right, it's like I said, Weierstrass is the one who really codified the epsilon arguments, but they were being made. Right, so, for example, Bolzano was doing it. Cauchy was making epsilon arguments. He was making this sort of, we can get the distances to be as arbitrarily small as we want. I mean, that's effectively what Newton was trying to do with his ghosts of departed quantities thing that he was into. And even if you go back to the Greeks, I mean, that's effectively what Archimedes was doing. Right, it kind of gets a little overstated how much Archimedes really knew. He only computed the area under a parabola, and he basically used a limit to do it. So it does kind of get overstated that he, effectively knew calculus, but not exactly, but he sort of did. But anyway, so Cauchy kind of saw that there was a flaw of kind of this formal investigation of limits of sequences, because you kind of need to know what the limit is in order to make these sort of epsilon arguments work. So he wanted a tool that allowed him to talk about a convergent sequence without actually addressing its limit. And that's going to be our goal. We are going to actually prove that Cauchy and convergent are equivalent to each other. So that's quite nice. That gives us a way of talking about convergent sequences without ever actually knowing what the limits are. Right, and note, the way a Cauchy is set up is very similar to how a convergent sequence is set up. Given an epsilon, there is an n, so some stuff happens. But note, it's purely a property of the sequence. It's not pulling in this other real number to the party. So, and as we will go forward, especially with series, Cauchiness allows us to get some pretty sweet proofs. Alright, so let's get used to working with the idea of Cauchy. And specifically, we'll prove our favorite sequence is Cauchy, 1 over n. Alright, so given an epsilon, we find our capital N, and the stuff happens that I want to happen. It's that easy. Right, let's unpack it a little bit more. Right, so given an epsilon, we know that we can get 1 over n to be less than epsilon. I have an epsilon over 2 because by my powers of clairvoyance, I know I'm going to add it up twice. That shouldn't be too shocking because, hey, I've got 2 terms. So if you pick n and m bigger than n, this distance is always less than or equal to their sum. And each one of these is less than 1 over n because n and m are chosen bigger. And they add up to 2 over n, and there you go, we get our epsilon. Beautiful. All right, so note, very similar to how we proved 1 over n converges to 0. But note, we just directly work with the sequence now. Given an epsilon, I find my n and show them a sequence has this desired property. That eventually the terms of the sequence get arbitrarily close to each other. Right? So, and if you think about where how 1 over n looks, right, so you get 1, then a half, then a third, then a fourth, then a fifth, then a sixth, then a seventh, then an eighth, then a ninth, then a tenth. And eventually, right, 1 over 100, everything after 1 over 100 is like on top of each other, basically, you know? So that's the idea of Cauchiness. These sequences are clustering around something. So maybe they have a limit. All right. Okay, so that's going to be our goal. And the good news is that we've basically already proven the hard part. We just had a couple of things we need to verify. So the first thing we're going to verify is that much like convergent sequences, Cauchy sequences are bounded. And as you'll see here, the proof is effectively the same. So by the Cauchiness, I can find an n so that my terms in my sequence get within 1 of each other. And we'll create our maximum of the terms of the sequence, and then a final term that we just throw in. And now note here, before this was the limit plus 1, and now instead of the limit, I just pick the nth term of the sequence, the point in which the Cauchiness kicks in. And then the argument is as before. So when n is less than n, then b is bigger than all of these, so that's it. And once n gets bigger than n, and by the Cauchiness, this is less than 1, so then I sneak in a plus 0, triangle inequality, and hey, that last term right there is less than or equal to b, so all of them are less than b in absolute value. So every Cauchy sequence is bounded, and the proof is identical, basically. So note, right, 1 over n converges to 0, we have verified that it's Cauchy, right? Similar proof. Convergent sequences are bounded. Well, so are Cauchy, and the proof's basically the same. So, right, this hope, this idea of being able to work with a sequence and basically have it be convergent but not know the limit, that's a very powerful tool. It's going to make life super easy. And speaking of convergent sequences, something we just discussed was that a convergent sequence can have convergent a sequence can have convergent subsequences, but be a divergent sequence. But something we saw was that if you are convergent, well then your subsequences have to be all convergent to the same thing, and a similar thing is true for Cauchy sequences. So here we see something incredibly powerful. If I have a Cauchy sequence that has a convergent subsequence, now, if I have a plane sequence that is a convergent subsequence, then I can't really say anything other than, well, I got a convergent subsequence, and that's it. A Cauchy sequence having a convergent subsequence means that my Cauchy sequence must actually converge to the limit subsequence. And now if you're immediately jumping up and down and going, hey, Cauchy is bounded, that means I have convergent subsequences. Shh, don't spoil it. We're getting there. Alright, so we're going to prove now that every Cauchy sequence that has a convergent subsequence must actually be convergent. How about that? So, let epsilon be greater than 0. By the Cauchiness, there's an epsilon over 2. And by the convergence of the subsequence, there's an m, so that we get within epsilon over 2. Okay, so we do our usual thing of taking the maximum of the n and the m. Let k be bigger than j. Alright, well then k is bigger than m. So, this applies. And n sub k is bigger than k, so remember that key property of subsequences. And k is It's bigger than j, which means it's bigger than n, so n sub k and k are both bigger than n. So when I look at this difference, which I'm trying to show is less than epsilon, I can sneak in the subsequence term. This must be less than epsilon over 2 by this. And this right here must be less than epsilon over 2 by the Cauchiness. Really beautiful, right? This is a tight proof. I love it. This is so cool. All right. So we have now verified that every Cauchy sequence with a convergent subsequence itself must be convergent. In fact, it converges to whatever that subsequence does. And again, the alarm bell should be going off in your head. Well, if I have a Cauchy sequence, I know it's bounded, which means I have access to convergent subsequences by Bolzano-Weierstrass. And that leads us to the big theorem for today, the last theorem for today. Like I said, this is a much shorter video, but what's on display here is incredibly powerful. Convergence and Cauchy are the same thing. So if a sequence converges, it's Cauchy, and if a sequence is Cauchy, it converges. Beautiful. So this is called the Cauchy completeness of R, and this is representing an idea that you'll see if you go further in your analysis life. This is a broader topic called completeness, and completeness turns out to be very powerful. Because completeness basically allows you to get limits of things without ever actually knowing what the limit needs to be. And that's an incredibly powerful tool. And it's something that is very unique to the real numbers. In fact, so when you do go further in your math life and you do talk about completeness of other math structures, almost always you use the fact that the real numbers are complete. So yeah, all right. Well, the good news is that we've basically done this proof. Specifically, the reverse direction is Cauchy sequences are bounded, bounded sequences have convergent subsequences, and Cauchy sequences with convergent subsequences must be convergent. So the only thing we really need to do here is the forward direction. Suppose you do converge, prove that you must be Cauchy. So suppose that you've got a convergent sequence. Let's let epsilon be given. What do I know? Well, I know that I get within epsilon over 2 of my limit. I have my capital N, so pick n and n bigger than capital N. The triangle inequality strikes one more, and we get less than epsilon, so any convergent sequence is in fact Cauchy. So I've got a fun little story about this. My advisor had me proctor one of his analysis exams. And I knew a few of the people in the class, and one of the things he asked them to prove was every convergent sequence is Cauchy. And after the exam, his name was Stephen. Stephen comes up to me, and he goes, I know every Cauchy sequence is convergent. I can do that proof for you right now. And he was like, I don't know why every convergent sequence is Cauchy. So he had the other proof ready. He had the every Cauchy sequence is convergent. My advisor tricked him a little bit by giving him the other one, and he was like, how do you prove that? And then the second I wrote this, like all the color drained out of his face, and he was like, oh my god, it's that easy, isn't it? And I was like, yeah, sorry. So he was ready for the reverse direction. He was ready for the much more complicated proof. But the easy one, he totally blanked. And I was like, oh no, that sucks, dude. He works for, Steven works for MATLAB now. Last I knew, anyway. I don't know if he's still working. A bunch of people that I went to school with all work in MATLAB now. At least 4 that I know of. Last I knew, I haven't talked to them in years. This is well over 10 years ago. Yeah, who knows? But anyway, yeah. So this every convergent sequence is Cauchy is like forever in my brain now because I was like, he was so like distraught too because he was like, I know how to do the harder direction. I don't. How do you do the easy one? And it's great. All right. Well, speaking of the harder direction, let's do it. And like I already said, the good news is that we've done it. Right. Suppose my sequence is Cauchy. It's bounded. By Bolzano-Weierstrass, there's a convergent subsequence. If your Cauchy sequence has a convergent subsequence, it must be convergent. Proof's over. Now, this proof right here, this is a great example of the kind of proofs that you hit a point where you start standing on the shoulders of giants, right? Cauchy, we took the time to prove that means it's bounded. We spent, like an hour talking about why bounded sequences have convergent subsequences. And we took the time to prove that if you're Cauchy and you've got a convergent subsequence, then you must be convergent to begin with. So in particular now, we know that every Cauchy sequence has a lim-inf and a lim-sup, and the lim-inf and the lim-sup have to actually be equal to each other. And in fact, that's the limit of it. Cool. Beautiful. All right. But yes, this is a great example of the sort of, bang, bang, boom, proof over. A good three-liner, but 3 lines with a lot of time and effort going into them. And, and those are the sort of proofs you will make more and more as your life goes on, where you kind of have more theorems at your disposal, and you kind of, so these are always fun proofs to make. I always love these sort of ones. My advisor, speaking of him, he was always a big fan of those. Those were his favorite kind of proofs, where he's like, this is one line from abstract algebra. And it was something where it was like you had to use the first isomorphism theorem in like a clever way. So he loved things like this, where it's like proving a Cauchy sequence is convergent. It's one theorem, and it's Bolzano-Weierstrass, just applied very carefully. So there's a bit more work. And speaking of that, like getting a statement proven very quickly and easily. That's a goal in math, to do that. So, even if you don't, prove anything new, if you come up with a quick way of proving it with just a couple of neat little theorems, there's super value in that. In my own branch of research, there's a guy named Gelfand, and that was sort of his huge claim to fame, is that he took this, 100-page monstrosity called Weiner's Lemma, and he just collapsed it down to a paragraph. Or he was just like, hey, you do this thing, and then you get this 100-page proof done, immediately. But it was one of those, there was a lot of setup to just jump in with the one theorem, but very similar to what we did here. Now, like I said, yeah, there's value in that. So, hey, there we go. We now know that every Cauchy sequence is convergent, and vice versa. And that's pretty much the story for sequences. So, like I said when we first started, sequences are kind of, we kind of quickly go through them in Calc 2, but hopefully in this little week here you've seen there's some interesting and frankly some pretty cool proofs about sequences. But now, equipped with this, it's time to tackle. It's time to go back to Calc 2 and then slay those series dragons once again. This time, though, they're coming back a little stronger, because limits aren't good enough. We gotta use lim-sups, it turns out. Alright, well, so that will be next week's plan. So, with that, the story for sequences, for now, is over.